Good morning, children. In the previous class, we have studied about balanced and unbalanced forces, Newton's first law of motion, and inertia. You know, Newton's first law of motion states that every body continues in its state of rest or uniform motion along a straight line unless it is compelled by an external force to change that state. From this law, it is clear that a body is unable to change its state of rest or motion by itself. This property of the body is known as inertia. So, inertia means the tendency of a body to oppose or resist any change in its state of rest or uniform motion by itself. Inertia is the inherent property of all the bodies. Therefore, Newton's first law of motion is also called law of inertia. In today's class, we will learn about inertia and momentum, second law of motion, mathematical expression of second law of motion, and units of force. Now you know, inertia is the inherent property of all the bodies. Different bodies have different inertia. For example, consider an empty box and a filled box. Push both the boxes by applying an equal amount of force. Then you find that it is easier to push an empty box than a filled box. It means the filled box opposes more to change in its state of rest than the empty box. Therefore, heavier objects offer greater inertia than the lighter objects. Therefore, the inertia of a body is directly proportional to the mass of the body. It means if the body has more mass, then it has more inertia. If the body has less mass, then it has less inertia. Next, let us know about the momentum. If we consider the mass of a body and its velocity separately, then it has no practical significance. For example, the fast-moving empty truck is more dangerous than the standing loaded one. Another example, a bullet when placed on the hand of a person causes no danger, but when it is fired from a gun, it becomes dangerous. From these two examples, it is clear that a physical quantity, which is the product of the mass and velocity of a body, is more significant and fundamental than either velocity or mass taken separately. Newton called it as momentum. So, we can define the momentum of a body as the product of its mass and velocity. Momentum of a body is denoted by the symbol P. If mass of a body is m, its velocity is v, then its momentum p is given by momentum is equal to mass into velocity. Then we can write the momentum as p is equal to m into v. Since velocity is a vector quantity, so momentum is also a vector quantity. Therefore, we can write the momentum in the vector form as, the SI unit of mass is kg and the SI unit of velocity is meter per second. Therefore, the SI unit of momentum is kg meter per second. The CGS unit of mass is gram and velocity is centimeter per second. Therefore, the CGS unit of momentum is gram centimeter per second. Graphical representation of momentum. The first one, momentum velocity graph. The graph obtained by taking the momentum along the y-axis and velocity along the x-axis is a straight line. So, the momentum velocity graph shows the variation of momentum with velocity when the mass of a body is constant. Next, momentum mass graph. The graph obtained by taking the momentum along the y-axis and the mass along the x-axis is a straight line. The graph shows the variation of momentum with mass when the velocity of a body is constant. Next, let us know about momentum and second law of motion. According to first law of motion, the velocity of an object changes when an unbalanced force acts on the object. Therefore, the velocity of an object depends upon the amount of force applied. The change in momentum is not only determined by magnitude of force but also by the time during which the force is exerted. Next, Newton's second law of motion states that the unbalanced force applied on a body is proportional to the rate of change of momentum produced in the body. It can also be stated as the rate of change of momentum of a body is directly proportional to the unbalanced force acting on the body, and the change in momentum takes place in the direction of unbalanced force. Therefore, F is proportional to dp by dt, where dp is equal to change in momentum and dt is equal to time taken for this change in momentum. Next, let us know about the mathematical formulation of second law of motion. Consider a body of mass m moving with initial velocity u. Let a force F acts on the body for time t so that the velocity of the body after time t is v. Since the mass of the body is m and its initial velocity is u, therefore the initial momentum of the body is mu. And the mass of the body is m and its final velocity is v, therefore the final momentum of the body is mv. Therefore, change in momentum of the body is pf minus pi. You know, pf is mv and pi is mu. Therefore, the change in momentum of the body is equal to mv minus mu. Here, we can take m common factor. Therefore, the change in momentum of the body is equal to m into v minus u. The time taken to change this momentum is the difference of the final time and the initial time. The final time is t and the initial time is 0. Therefore, the time taken to change this momentum is equal to t minus 0. T minus 0 is equal to t. Therefore, the rate of change of momentum is equal to change of momentum by time taken. Therefore, the rate of change of momentum is equal to change in momentum by time taken. You know, the change in momentum is m into v minus u and the time taken is t. Therefore, the rate of change of momentum is equal to m into v minus u by t. According to Newton's second law of motion, the force applied on the object is directly proportional to rate of change of momentum. The force applied on the object is F and the rate of change of momentum is m into v minus u by t. Therefore, F is proportional to m into v minus u by t. Consider this as equation 1. V is equal to u plus at from first equation of motion. Then we can write it as at is equal to v minus u and a is equal to v minus u by t. Consider this as equation 2. From equation 1 and 2 we get, therefore F is proportional to ma, or we can write it as F is equal to k into m into a, where k is constant of proportionality. If F is equal to 1 unit, M is equal to 1 unit and A is equal to 1 unit, then the value of K is equal to 1. Therefore, we can express F is equal to KMA as F is equal to MA. Therefore, the force acting on the body is directly proportional to its mass and its acceleration. Therefore, the force acting on the body is directly proportional to its mass and also its acceleration. Next, let us know about units of force. From Newton's second law of motion, we know force is equal to the product of the mass and acceleration. If M is equal to 1 unit and A is equal to 1 unit, then F is equal to 1 unit. Therefore, force is said to be unit force if it produces unit acceleration in a body of unit mass. We know the force is equal to the product of the mass and the acceleration. The SI unit of mass is kg and the SI unit of acceleration is meter per second square. Therefore, the SI unit of force is kg meter per second square. 1 kg meter per second square is equal to 1 Newton. Therefore, 1 Newton is equal to 1 kg meter per second square. If a force acting on a body of mass 1 kg produces acceleration of 1 meter per second square, then the force is said to be 1 Newton. Next is CGS unit of force. The CGS unit of mass is gram and acceleration is centimeter per second square. Therefore, the CGS unit of force is gram centimeter per second square. The CGS unit of force is dyne. Therefore, 1 dyne is equal to 1 gram centimeter per second square. If a force acting on a body of mass 1 gram produces acceleration of 1 centimeter per second square, then the force is said to be 1 dyne. Next is relation between Newton and dyne. We know that 1 Newton is equal to 1 kg meter per second square. You know 1 kg is equal to 1000 gram and 1 meter is equal to 100 centimeter. We can write 1000 as 10 to the power of 3 and 100 as 10 to the power of 2. Next, 10 to the power of 3 into 10 to the power of 2 is equal to 10 to the power of 5. So therefore, 1 Newton is equal to 10 to the power of 5 gram centimeter per second square. You know, 1 gram centimeter per second square is nothing but 1 dyne. Therefore, 1 Newton is equal to 10 to the power of 5 dyne. Next, let us know about the applications of Newton's second law of motion. A karate player breaks a pile of tiles with a single blow. As the karate player strikes as fast as possible, the entire momentum of the hand is transferred to the pile of tiles in a very short time. Therefore, the rate of change of momentum is very large that causes a strong force to act on the pile of tiles. Hence, the pile of tiles breaks. Another example, a high jumper tries to increase the time of his fall on the ground by extending his legs in the forward direction. Therefore, the rate of change of his momentum decreases. Therefore, less force of ground acts on the feet of a jumper and he is hurt less. Another example, A wrestler tries to increase the time of hit on the ground by bending his body forward. In this way, the rate of change of his momentum decreases and he feels less amount of force on his feet. Therefore, he is not hurt. Another one, a cricketer pulls his hands backward while catching a ball. In this way, the player increases the time of change of momentum of the ball. Therefore, the force exerted on the hands decreases and the player feels reduced impact of ball on the hand. These are the few applications of Newton's second law of motion. Okay children, let us continue in the next class.